So sometimes we call latches flip-flops, and usually that's when the synchronous circuit has a clock. When there's no clock on as oops, when there's no clock on a latch, then the circuit is called asynchronous. And when there is a clock symbol, it's synchronizing with a clock. So we call it a synchronous circuit. So let's take a look at a synchronous circuit. In reality, most digital systems are synchronous. And why we do that, it just means that you add another input. So let's say this is a flip-flop. And of course, it just has output Q and Q naught, just like before. And then you have your inputs that they could be S and R. So it can be S and R or J and K. We haven't talked about that yet. And then another input is added, and it usually looks like this. It usually has a little arrow inside, and that's clock. And what that means is just that, yes, you're taking those inputs S and R, and they're going up and down, whatever is happening. And but then you're also putting in this clock signal, and the clock signal is continuously like this. And what this does is it says, hey, don't calculate Q output until the rising edge or the falling edge of a clock. So what I'm drawing here is a rising edge. And this just means that we kind of know the value of Q is consistent, and we know that we're going to calculate Q at a certain period of time, at a certain interval. And that is to solve some problems. For example, S in the real world, look, it doesn't actually rise exactly like we show in the diagrams, and it doesn't fall exactly like we show either. So there's a little bit of a lag in the signals that go into these systems. So I don't want sort of here, here S is falling a little bit, R is rising a little bit. Those voltages could be added together, and I don't know what the answer of Q is. Well, if I have a clock signal, well, I knew what the answer was here on this rising edge of the clock. And I knew what the answer was here because those values have settled. So the clock signal makes it more repeatable and predictable. And we know when to sort of open the gate and read our input signals. So the clock signal needs to be a consistent signal on and off at a certain time. And that makes our digital system a little bit more predictable. Zero, it goes from 0 to 1, and it is edge triggered. So this is the rising edge of a clock signal. So this is rising edge. So we can trigger a flip-flop on the rising edge, or we can trigger a flip-flop on the falling edge. If we trigger it on the falling edge, it means it's this time in which we let the S and the R values become valid. So this is the falling edge. So now if I ask you to analyze a flip-flop and I give you the inputs for S and the input for R as it changes over time, I have to tell you a few things. I have to tell you if it's a NAND gate or a NOR gate latch. Then I have to tell you if it has a clock signal or not. Then I have to tell you if the clock signal is triggered on the rising edge or the falling edge. And I have to tell you what were the initial values of Q. Were they 0 or were they 1?